Welcome to Ask and Learn.
So the first question is asking us to write a balanced equation for the combustion of octane. So combustion reactions are always going to have oxygen gas, and they're going to combust into CO2 and H2O. And so if we go ahead and try to balance this out, well, we can see we've got 8 carbons on the left, which means that we need 8 carbons on the right as well. We've got 18 hydrogens on the left, so on the right we need 18 hydrogens as well, which means that we need 9 waters. And therefore the number of oxygens we need, so the oxygens on the right, we've got 8 times 2 is 16, plus 9 more is 25, so we're going to need 25 over 2 oxygens in order to balance this out. So that's a balanced equation. Ideally, I would multiply all of those through by 2 as well, because we don't like to have non-integers. So we'd end up with a 2, 25, 16, and 18. So part B, is saying that if we assume that gasoline is 100% isooctane, and the density of isooctane is 0.792 grams per milliliter. Then the question is, what mass of CO2 in kilograms is produced by burning 4.6 times 10 to the 10th liters? So that's 4.6 times 10 to the 10th liters. And the question is, how many grams of CO2 do we create? So what we're going to need to do here is let's convert our 0.792. Actually, let's convert the liters here into milliliters. So we're going to do 10 to the 13th milliliters. So 0.792 grams per milliliter times 4.6 times 10 to the 13th milliliters. And this is to figure out how many grams of C8H18 we have. So let's multiply this out. 792 times 4.6 times 10 to the 13th power gives us 3.64 times 10 to the 13th grams of C8H18. So that's not what the question is asking, though. The question is asking how many grams of CO2 do we get out of this. So we're going to need to do some stoich here. 3.64 times 10 to the 13th grams of C8H18. And the molar mass of that, 12 times 8 is 96, plus 18 is 114. 114 grams per mole. And for every 2 moles of C8H18, we make 16 moles of CO2. And for every 1 mole of CO2, we get 44 grams of CO2. So multiply all that out using our ladder method here. We get 3.64 times 10 to the 13th power, we're going to divide by 114. We're going to multiply by 16 over 2. And we're going to multiply by 44. And the final answer we get there is 1.1 times 10 to the 14th grams of CO2, or 1.1 times 10 to the 11th kilograms of CO2. So that's part B. To move on to part C, what is the volume in liters of this CO2 at STP? So let's go ahead and get a new page here. So we had 1.1 times 10 to the 14th grams of CO2. We want to get to volume in liters. So let's get it back into moles by dividing by the molar mass of CO2, which is 44 grams per mole. So that gives us 2.55 times 10 to the 12th moles. And each mole is 22.4 liters at STP. 10 to the 12th mole times 22.4 liters per mole (5.72 times 10 to the 13th liters. So that is the amount of CO2 that we're going to create. And then finally, the question is how many moles of air are necessary for the combustion of 1 mole of isooctane, assuming that air is 21% O2 by volume, and what is the volume in liters of this air at STP. So I'm going to go ahead and get another fresh page, even though we've still got some space here because we're not using any of these previous calculations here. So we have 1 mole of isooctane. We know that to combust 1 mole of that, we need 25 over 2 moles of O2. And so if for every 21 moles of O2, we have 100 moles of air, that gives us 25 divided by 2 is 12.5 times 100. 1250 divided 21 gives us 59.52 moles of air. And then finally, what is the volume in liters of that air at STP? Well, just like before, we can take our 59.52 and multiply it by 22.4 moles per liter, and that'll give us 1,333 liters of air.